Good afternoon, students. This is again Pragnesh Polara from Dr. Subhash Technical Campus, Junagadh. In this session, we are going to discuss about the topics of eigenvalues and eigenvectors. In the last lecture of this topic about the eigenvalues and eigenvectors, we have already discussed how to find the eigenvalues for the given matrix, how to find the eigenvectors for the given matrix, what is the meaning of eigenvalue, what is the meaning of eigenvector for the any given matrix. Today our idea is to discuss the topic of Cayley-Hamilton theorem and then to find the diagonalization of any matrix. Before we move ahead and discuss about this Cayley-Hamilton theorem and the process of diagonalization, before that I want to explain some properties of eigenvalues and eigenvectors in front of you. Okay, if we look at the PPT here, today this is the content of this lecture, in which we will discuss the Cayley-Hamilton theorem and the diagonalization of a matrix and the reduction of a matrix to the diagonal form. First of all, let us look at these properties of eigenvalues. The first one is the sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. Why I am explaining all these properties? Because these properties are very much important for the exam point of view, because we all know how to find the eigenvalues and eigenvectors, but if there is any twisted question related to property, then we must know about the properties of eigenvalue to solve that example. So the first property is the sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. The second property is the product of the eigenvalues of a matrix A is equal to its determinants. Note that the product of eigenvalues is equal to the determinant of the given matrix, right? The third property is if lambda is an eigenvalue of a matrix A, then 1 upon lambda is the eigenvalue of A inverse. Sometimes you have asked to find the eigenvalue of A inverse and you have given only A, so you don't need to find any A inverse to find the eigenvalue of A inverse. You just need to find the eigenvalue for the matrix A, and 1 upon lambda will be the eigenvalue of A inverse. If lambda is an eigenvalue of the orthogonal matrix, then 1 upon lambda is also the eigenvalue of that matrix. Okay, so this is the fourth property. In the same way, this is the property again, that if lambda 1, lambda 2 up to lambda n are the eigenvalues of A, then k into lambda 1, k into lambda 2 up to k into lambda n are the eigenvalues of the matrix Ka, where k is non-zero scalar, right? So sometimes you have asked to find the eigenvalue of 2a or eigenvalue of 3a, so you just need to find the eigenvalues of A, then multiply all the eigenvalues with the given scalar number, so you will find the eigenvalues of k into A, where k is any non-zero scalar. In the same way, here in the second, 1 upon lambda 1, 1 upon lambda 2 up to 1 upon lambda n are the eigenvalues of the inverse matrix A inverse, right? So if we want to find the eigenvalues of A inverse, we can easily find the eigenvalue of A, which is lambda 1, lambda 2 up to lambda n, then 1 upon lambda 1, 1 upon lambda 2 up to 1 upon lambda n are the eigenvalues of the inverse matrix, right? The third property is also important here, that if lambda 1, lambda 2 up to lambda n are the eigenvalues of A, then lambda 1 raised to p, lambda 2 raised to p up to lambda n raised to p are the eigenvalues of a raised to p. So if you have given the matrix A and you are asked to find the eigenvalues of a cube, for example, then the p is equal to 3. So you don't need to find a cube, you just need to find the eigenvalues of a, and after giving the lambda 1 cube, lambda 2 cube, lambda 3 cube, you will find the eigenvalues of a cube, okay, where p is any positive integer. So in this way we can solve the example, which are also, they are quite easy to find the eigenvalues and eigenvector, but sometimes the examples are twisted and you need to use the property to solve that example. So these are the most important properties to solve some twisted example of finding eigenvalues and eigenvector. So this is about the properties of eigenvalues. So now let us look at the Cayley-Hamilton theorem, which is given in the PPT. This is the statement that is every square matrix satisfies its own characteristic equation, right? I am repeating the statement that every square matrix satisfies its own characteristic equation. We know that the characteristic equation is a determinant of a minus lambda I is equal to 0, and then by solving this we will get the equation of lambda, and the statement is said that the every square matrix satisfies its own characteristic equation. That means if we replace lambda by a in the characteristic equation, then a also satisfies that equation. For example, if a is equal to n cross n square matrix, then it's like a11, a12 up to a1, and in the same way an1, n2 up to nn, that is n cross n matrix. Then the characteristic equation of a in the form of lambda, then phi of lambda is equal to a minus lambda I, that is the characteristic equation, that is equal to a minus lambda I is equal to 0. That is the characteristic format, that is a11 minus lambda, a12 up to a1n, a21, then a22 minus lambda up to a2n, likewise, okay. And the characteristic equation is equal to determinant of a minus lambda I, that is equal to 0. So okay, we will get the characteristic equation here, that is in the form of lambda m, that is the polynomial of degree n, right, where p0, p1, p2 up to pn are the coefficient of that polynomial. So we have here p0 lambda raised to n plus p1 lambda raised to n minus 1 plus p2 lambda raised to n minus 2 plus up to plus pn is equal to 0. That is the characteristic equation for the matrix A. So by the statement of the Cayley-Hamilton theorem that matrix A will satisfy this characteristic equation, if we replace lambda by A, then the characteristic equation will give us p0 a raised to n plus p1 a raised to n minus 1 plus p2 a raised to n minus 2 plus up to plus pn into I, that is the identity matrix, is equal to 0. So this is the idea of Cayley-Hamilton theorem. So here 0 is equal to all the polynomial of degree n, that is 0 is equal to, if we multiply the equation number 1 both sides with a inverse, then we will get the first term will be p0 a raised to n minus 1, because we have multiplied with a inverse, okay. So plus p1 a raised to n minus 2 plus p2 a raised to n minus 3, likewise plus up to plus pn a inverse, okay. So we will get if we simplify this matrix equation, then we will get a inverse is equal to 1 upon minus 1 upon pn into bracket p0 a raised to n minus 1 plus p1 a raised to n minus 2 plus up to plus pn minus 1 into I. So this shows that using the Cayley-Hamilton theorem we can easily find the value of A inverse for the any matrix A. Okay, so in this way we can also find the value of A inverse. Okay, so now this result, what this result gives us, this result gives the inverse of A in terms of n minus 1 power of A, and that is considered as a practical method for the computation of the inverse of large matrices. Okay, if we want to find the inverse, then using the Cayley-Hamilton theorem we can easily find the inverse of that given matrix. Okay, so this is very much important reason to find the inverse of any given matrix. Okay, so here let us look at one example of using Cayley-Hamilton theorem. The question is, verify Cayley-Hamilton theorem for the matrix A is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2, and hence compute A inverse. So here first of all we need to verify the Cayley-Hamilton theorem. That means the matrix A, we need to show that the matrix A will satisfy the characteristic equation, right? Then using that characteristic equation we need to find A inverse. Okay, so we have given the matrix A. Here the characteristic equation will be A minus lambda I is equal to 0. So we will get A minus lambda I, that is equal to 2 minus lambda minus 1 1 minus 1 2 minus lambda minus 1 1 minus 1 2 minus lambda, that is equal to 0. This is the determinant of this one is equal to 0, which will be the characteristic equation. By simplifying this one, we all know how to simplify the determinant, how to expand the determinant. So by expanding this 3 cross 3 determinant, we will get lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. And the simplification of this is on the students. Students should try to expand the determinant and find the characteristic equation is equal to lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. So this is the homework for the students, that to find this equation. Okay, so characteristic equation will be lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. Here we need to verify the Cayley-Hamilton theorem. So we need to prove that if we replace lambda by A here, then A cube minus 6A square plus 9A minus 4 is equal to 0. That we need to prove, right? So what we need to prove here, that to verify the Cayley-Hamilton theorem we have to show that A cube minus 6A square plus 9A minus 4I is equal to 0. We have A is given, so using that value of A we will find first of all A square, then A cube, then 9 into A, and replacing, then substituting all these values in equation number 1. Here equation number 1 is A cube minus 6A square plus 9A minus 4I, that is the left hand side, and we need to prove that all the simplification will give us the null matrix, right? So here A is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2, and A square is equal to A into A. And now students should remember how to multiply the two matrices. Okay, so here I want to remind you how to multiply the matrices. If we look at here practically, we have A square is equal to here 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2, and this is A into A. So this is again 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. If you want to multiply these two matrices, then the column of this matrix must be equal to the row of the matrix, second matrix. So here, so we will multiply here. First of all, we will concentrate on the first row, and we will multiply the corresponding element of this first row with the corresponding element of this first column, right? So here we will get, first of all, I will multiply, thus concentrate on my hands. Here we will multiply 2 with 2, that is equal to 4, plus minus 1 with minus 1, this minus 1 into minus 1, that is plus 1, plus 1 with 1, that is 1 into 1, that is equal to 1, right? Again, now we will change the column of the second matrix. So now we will multiply 2 with minus 1, that is minus 2, then minus 1 into 2, that is minus 2, then 1 into minus 1, that is minus 1. Again we will change the column. Now this is the third column, we will multiply it with the first row. So 2 into 1, that is 2, minus 1 into minus 1, that is plus 1, then 1 into 2, that is 2. Now all the three columns are here. Now we will change the row. Now we will concentrate on the second row, and we will multiply with the first column, second column, and third column. So quickly, if we multiply here, then we will get minus 1 into 2, that is minus 2, plus 2 into minus 1, that is minus 2, and minus 1 into 1, that is minus 1. Okay, the same way, minus 1 into 1, that is plus 1, 2 into 2, that is plus 4, minus 1 into minus 1, that is plus 1. Again, minus 1 into 1, that is minus 1, 2 into minus 1, that is minus 2, minus 1 into 2, that is minus 2. In the same way, again I will change the here row, then now I will concentrate on the third row. So 1 into 2, that is 2, minus 1 into minus 1, that is plus 1, 2 into 1, that is 2. The same way, 1 into minus 1, that is minus 1, minus 1 into 2, that is minus 2, sorry, minus 2, 2 into minus 1, that is minus 2. In the same way, 1 into 1, 1, minus 1 into minus 1, that is plus 1, 2 into 2, that is